Welcome everybody. Part 1, a different approach for the twin prime theorem. My name is Manuel P. Rodriguez Velasco and I am a mechanical engineer. And this study was presented December 22, 2022 at the Polytechnic University of Puerto Rico to a group of professors of engineering and science and for an audience. We're going to study the prime numbers by their cycles. All prime numbers have a cycle. I am dividing the cycles in tens. Here you have the cycle of 3. But first, you gotta remember that all prime numbers, except 2 and 5, they end in 1, 3, 7, or 9. All the numbers, the last digit, gotta be one of those to be able to be a prime. It could be not. So the numbers that you see there on the tens are the 3, the 9, the 21, and the 27. The other numbers that ends in 1379 that are not there could be primes. Like in the 10 from 1 to 10, gotta be the 1 or the 7. In the 11 to 20, gotta be 11, 13, 17, 19. And in the 21 to 30, gotta be the 23 or the 29. Any of those could be a prime, but not necessarily. The tenth of the middle is what I call a ten full of primes, or a prime 10. If we repeat the cycle several times, the same sequence gonna be repeated. I show you. Here you have the cycle of 3 with 3 iterations. It is repeated 3 times. In this one will be 1, 2, and 3. You can see that they have the same arrangement of numbers and of tens. All those numbers that you see there won't be primes, except for the 3. So you can have here 21, 27, 33, 39, and here in the last one, 81, 87. All of them that ends in those numbers won't be primes ever in every cycle of 3 when they keep repeating. The other numbers could be prime, but not necessarily. That depends on the next cycles of the primes. So gonna come the cycle of 11, the cycle of 13, cycle of 17, and it could affect other numbers in the cycle of 3. So we will see that in a moment. Here you have the cycle of 7. And how you can see, it has also 4 numbers that they represent numbers that won't be primes in the iterations of 7. How I told you, in the cycle of 3, the 49 was to be a prime number. But the cycle of 7 has 7 times 7, 49, and is here. So that number won't be a prime. That's why we have to check all primes to be sure what is a prime and what is not. This is the cycle of 7 with 2 iterations. How you see, they have the same numbers in the same positions of the cycle. So for infinity, those numbers in that positions of the cycle won't be primes ever. Here you have the cycle of 3 and the cycle of 7 together. So now you can calculate prime numbers looking in the same way that we did before. Here, 23 and 29 will be primes because the numbers are not here, right? There is no 3, there is no 9. And here, the 53 and the 59 will be primes. But there are other cycles. The cycle of 11 is the next one. And in this 10, 11 times 11 is 121. So in the cycle of 3 and 7, 121 was to be a prime. But because it's coming the cycle of 11, won't be a prime anymore. So that's the difficulty of knowing which are the prime numbers. Because every time that comes a different prime, will have a different cycle, and we cannot predict which ones will stay as a prime and which ones not. So here we have the first cycle of 7 that starts, for example, with the cycle of 3 in the first 10 of 3 and the first 10 of 7. And now it's different. Here is the start of the cycle of 7, iteration number 2, and look, now it starts together with the second 10 of the cycle of 3. Here it starts with the first 10 of the cycle of 3. Here starts with the second 10. And in the next cycle of 7, that is here, it starts here, it starts together with the third 10 of the cycle of 3. So I saw that they were combining differently. Every 10 was having different combinations of different 10s of both cycles. And I realized that they were combining in all possible combinations of 10. All possible combinations of 10 without repeating until they form a new cycle. So you can see here that we have the cycle of 3 from 1 to 30, the cycle of 7 from 1 to 70, and you see that they're gonna cover all type of combinations, and they're gonna go like this. I show you now. So first, gonna start here. That's the first 10 of 3 gonna combine with the first 10 of 7. And then now you here have the second 10 of 3 with the second of the 7, third one of 3 with the third one of 7, and now changes here to the first of 3 with the fourth of 7, second of 3 with the 5 of 7, and again here the third of 3 with the 6 of 7, and here the last 10 of 7, the 7th, with the first 10 of 3. And now it keeps combining, so it starts here again, and then here, so you can see, and then they're gonna cover this, and then this, and we'll continue here, and all types of possible combination without repeating are formed, okay? So it's like they go in diagonals. That will change with other cycles. You can see also that here comes now the cycle of 11, and 11 times these two cycles together, the merge of the cycle of 7 and 3. So that 11 times gonna make all possible combinations of the cycle of 3, 7, and 11, all combinations of 10s, okay? So now we have the symmetric cycles of primes. We found that all cycles of primes are symmetric. They combine every 10 combination, and we're going to study that. First of all, I have new variables and names, so you can familiarize with them. Pn is prime number not 1 to 5 or 5 unless specified. This is the cycle of prime n, cycle of that prime alone. This is the sample, that is the cycle of 7, of length Pm times 10. They will be the cycle of Pn1 to until n, all the primes you put there. The prime 1 will gonna be 3 always, and prime 2 gonna be 7. Okay, so you can keep adding primes to the cycle and merging in new cycles. Okay, this is the cycle from 3 to Pm, right? From prime number 1 to Pm. So this is an abbreviation of this here. And this is the cycle of 3 and 7. It is a symmetry. It has a symmetry on the middle here, always in a prime 10. And in the beginning and the end, in the second 10 here, another prime 10, and in the second 10 of the end, another prime 10. But it's a symmetry everywhere. 173 here, you have 3, 7, 9 here. Prime 10, prime 10. 3, 9, 1, 7. 3, 9, 1, 7. A 1 here gotta be a 9 in the other side. A 1, 7 here gotta be a 3, 9 in the other side here. 1, 7 gotta be a 3, 9 here. 7 gotta be a 3 here. 3, 9, 1, 7, 1, 3, 9, and 1, 7, 9, and a prime 10 on the middle. All cycles gonna do this. All cycles gonna have a symmetry on the middle. That will be a prime 10, 2 prime 10s in the second of the beginning and the end, and all 10s gonna be a symmetry. So we're gonna study how they behave and their characteristics, and we're gonna evolve with this. Here you have the cycle of 3 and 7 merged together, like in the previous slide, this one. And now you have the prime numbers underneath. There is an exception always in the first 10, because in the cycle of 3 and 7, these numbers won't be primes in every iteration. But in the first 10, they will be primes, the 3 and the 7. Okay? So they are like primes here. The number 1 is an exception always in every cycle of primes, because it will be a potential prime in the first 10 of every iteration of every cycle. Now you can see that I divided this in a real composition of number and unknown composition of numbers. Because there is coming another prime cycles like the 11. You have to know that 11 times 11 is 121. So here was the 121 as a potential prime. But because the cycle of 11 will not be a prime anymore. Same will happen with other cycles, like the cycle of 13. 13 times 13 is 169. Here was like potential prime. But when comes the cycle of 13, won't be anymore. So I know that from here to 1, all these ones, in the cycle of 3 and 7, I can know which are the primes, because the cycle of 11 won't affect them, neither any other cycle from a bigger number, right? A prime bigger than 11. So until 120, we can calculate all the primes. All these ones will be primes. But after that, we have to calculate another cycles like 11, 13. In the cycle of 7, 3, and 11, if we merge the cycle of 11 with the cycle of 3 and 7, we will know that until 160, we will know which are the primes. Because in 169, won't be prime anymore. Really, until 169, lower than that, we will know that they are not primes. So 167, 163 will be primes, right? So that will be happening with any coming new prime cycle, new prime number. So we have some new terms. Here you have the prime 10. Prime 10 is a 10 that has no any number. When you merge cycles, they're gonna stay like it has no number. Here is the start of cycle 11. These are potential primes, 263 to 669, because there is no 3 and no 9 in the 260s 10. So that's how we're gonna call them potential primes. Are primes numbers that can be primes, but could be affected by other prime cycles. Here is this one, the 9 here is a flip potential prime. When you have, for example, in the 3 and 7 cycle, you have no 9 there, but it comes the cycle of 11 and flips the 9, the 319. So that won't be a cycle anymore. So we say that it's being flipped. Overflip is here. Is when comes another cycle of another prime. So in the cycle of 3, it was already flipped. But now comes the cycle of 7, and it's overflip, because that's repeating, and that will be important for later. Now we come for the important part. This one here is not a real prime cycle, but I put it as an example. Here we have the prime time of the cycle of 3 that will combine with the prime times of the cycle of 7, so they're gonna create more prime times, and then they're gonna combine with other prime cycles, with the prime times of the other prime cycles, so the prime time combinations are growing exponentially. Then you say, why we don't see it so often? Because they're gonna come very, very far away. They're gonna keep combining. These are signals that they will come to the real number line. So all combinations of prime times and prime times, we make a pool of prime times inside the symmetric cycles in the parts that haven't come out to the real number line yet. If you calculate the middle of all cycles, for example, the cycle of 3 and 7 is 210, you divide it by 2, and you will have 105. If you put those numbers in the middle, here, they're gonna combine until the minimum common multiple, until 210, until 0, when you expand it to the left and to the right. And that will happen with all combinations of prime cycles. You can keep combining, and you will always have the symmetry line in the middle, and you will always be able to expand to the minimum common multiple in this way and to 0 in this way, and they're gonna fit perfectly. Doesn't matter how many prime cycles you have. That's why you're gonna have always a prime 10 on the middle. It's important to know that the length of the cycles, combination of cycles, every time you add the next prime number to merge another cycle, gonna grow very fast. But that doesn't matter too much. You can get in trillions very soon, but really the composition of primes and the proportion of primes doesn't change too much. So for every cycle, you know that the composition of that cycle gonna be in the real number line before the square of the next coming prime. So in this cycle here, you know that until here, this here and back will be in the real numbers. And in this cycle, you know that until here, that will be the square of the next prime number you're gonna have. And here in this, in Pn square, okay, you're gonna have this cycle, all prime numbers will be there. So every new cycle is mapping the real number line. So this gap will map this portion, comes next prime, will map this portion, next prime, gonna map this portion, and so on. And this is the gap of the cycle of Pn square minus Pn minus 1 square. This is the portion that will be mapped the real number line, okay, before Pn square comes. So what happens every time that comes a new cycle, that you merge a new cycle with the previous one? You have here the cycle of 3 and 7, and when comes the new cycle, that will be the from 3 through 11, this is the triangle that is making. Really, it's a curve, right? But I put it like this. So you will have 11 times the cycle of 3 and 7 together with the cycle of 11 to form a new cycle, a new merge cycle. They're always gonna be symmetric. And look, now the length will be 2310 from 210, that was the previous one. And then gonna come another cycle, gonna come until 13, right? 3 through 13, and you have it here. I'm gonna have 13 times the cycle from 3 through 11, 13 times. 1, 2, 3, 4, 5, until 13. I'm gonna have again a symmetry in the middle, and the length gonna grow exponentially, 30,030. It's important to know that all cycles will start at 0, so they converge at 0. And for you mathematicians, maybe, right, has something to do with the zeta functions in the imaginary plane. I don't know. So in the middle, you see, they're gonna be always prime terms, but they all of them start at 0. When you make another cycle, gonna be a different cycle than the previous, but gonna start from 0. Okay. There will be no primes in the portion of primes of the cycle. In every iteration, they won't be primes. For example, if you have 3, 7, 11, 13, and 17 that merge in a cycle, you know that in next iterations, from here there, from the 17, they won't be primes in each iteration. Okay, they all will be primes here, but in every iteration at the beginning, they won't be primes in that tens, right? So until 17, won't be primes in the first and second 10 of every iteration. Here you have some information. Number E will be the number of iteration. You see 1, 2, 3 of that cycle, of the cycles. So we are clear for that. You know that the length will be multiplied by 10, and 10 is representing the 2 and 5, okay? In some way, we don't know how, but it's representing them. This is the prime 10 in the cycle of 3, just in the middle of cycle of 3. So now it comes the middle of the cycle of 7. This is from 1 to 70. That's the prime 10 in the middle of cycle of 7. So if you do like this and like that, there will be here. That's the next one, prime 10. That will be in the middle of the cycle of 7 and 3. Now comes the prime 10 in the middle of the cycle of 11 and 3. That's just in the middle. If you do like this, right, and we go through here, this is gonna connect here, and there will be there the connection of the 3 will be just inside that square that will be in the side will be the prime 10 of the cycle of 11, 7, and 3. This one here is the prime 10 in the middle of the cycle of 7 and the cycle of 11. I just showed this, so this will be good to do more research about this, but it will come the cycle of 13, the cycle of 17, and it will be good to know what is happening. One of the things, for example, is that you have 2 from the 3 here, 2 from the 7, that will be here, 2 and 2, and 2 here, the connection of this one here with the connection of this one here inside will be the prime 10 in the second 10 of the cycle of 3, 7, and 11. That's the prime 10s that are at the beginning of every cycle. And the other one will be up there, I think so. So that's interesting, okay? I will be here, but further story will be good for this. We have to calculate the prime cycles, the symmetric prime cycles by their own characteristics without being affected by other primes. For example, the cycle of 3 has a proportion of 8 divided by 30.2666. except in the first 10 of the cycle of 3 there will be 0.3 because the 3 is a prime also. To calculate the proportion of the cycle of 3 and 7, first a cycle of 3 plus modification of 7 and its prime flips. So the cycle of 3 and 7 goes from 1 to 210. That's 7 cycles of 3. Number of primes is, so I'm gonna calculate the number of primes for the cycle of 3 and 7 alone. So we are not taking account prime flips, okay, of other primes. 7 cycles of 3 multiplied by 8 primes per cycle of 3 plus 1. Plus 1 is because the 3 will gonna be a prime also. Minus the number of possible prime flip by the 7. Cycle of 3 to 7, it's a mistake here, gotta be another symbol there, right? Goes to 210. So until prime 29, prime 7 flips all the primes because 7 times 29 doesn't exceed 210. It's lower than 210. So there will be, this will be the proportion, 8 times 7. 8 primes per cycle of 3 times 7 cycles of 3 for 210 plus 1 by the 3, right? Minus 7 prime flips. So we will have a proportion of primes in the cycle of 3 and 7 without being affected by other primes of 0.38. So the equation of proportion of primes for all prime cycles will be the length of the cycle divided by the length of the cycle of 3 times 8 plus 1, because the 3 gonna be a prime, minus all the flips that occurs below the length of the cycle, and that has at least one member of the primes of the cycle, but not prime number 3. You have the equation there, and it's this one here. That is this equation simplified. The 30 is this length of the cycle of 3 times 8 primes per cycle of 3 divided by the length of the new cycle. So we take the 10 with the 30, and the 3, we're going to take out the prime number 1, that is the 3. So we get this equation. The important about this is that we're going to be comparing the characteristics of each symmetric cycle without being affected by other primes. So the characteristics of the symmetric cycles of primes, they are symmetric, of course. They start at 0. The first number ended in 1 and the last number ended in 9 on each iteration of perfect cycle is always a potential prime. Always a prime 10 in the middle of the cycle and in the second 10 of the beginning and end of any cycle. There is always a part of all the cycles that is in the real numbers line. There is a not real part of the cycles. There is a part of the cycle that is not real always. Okay. So now comes the prime tens theorem, a proposed solution for the twin primes theorem, proposed by myself, Manuel P. Rodriguez Velasco, mechanical engineer. There is an infinite number of tens with 4 primes. I believe most mathematicians will say no to this, but here is my proposed solution. So we're gonna go back to the creation of prime tens. You have here the prime 10 of the cycle of 3 that's gonna combine with the 3 prime tens of the cycle of 7 that will create the 3 prime tens in the cycle of 3 and 7. But then gonna come the cycle of 11. That cycle gonna have, you see here, 7 prime tens. And that 7 prime tens gonna combine with the 3 prime tens of the cycle of 3 and 7 with the 1, 2, 3. They're gonna combine to form 21 more prime tens. This chain of prime tens is an indication that far away they will appear. They will appear so far that computers can't reach them yet. They will be so far from each other. Of course, some of them will come to the real number line. It's a process. But they're gonna look like there is fewer and fewer of them. What I am saying is that they don't gonna disappear, that they don't gonna pull away forever, that they don't gonna be destroyed, because this is a process of creating. This is a process that every time you're gonna have more and more prime tens in the symmetric prime cycles that are underneath the real number of line. In the cycle from 3 through 11, this will be a prime ten. But we're gonna come another cycle that's gonna flip some of the numbers, so it will not be a prime ten. Anyway, this is gonna be combined to form another prime ten. Doesn't matter, gonna be flipped later. In that prime ten, the 221 number will be flipped and will not be a prime. The prime ten will not be a 10 full of primes, but it will continue combining with other prime cycles to eventually make a combination that will become a prime 10. This could be thousands or billions or trillions up in the real number line. In the real number line, sorry. So now we're gonna see how non-prime tens are created. Combinations that form non-prime tens. We have here the cycle of 7 and the cycle of 3 and 7. So you can see here the cycle of 11. The numbers in the cycle of 11, the tens that has numbers on them, they're gonna combine with all the tens of the cycle of 3 and 7. That is this one here, okay? So they're gonna form 84 more non-prime tens for the next cycle. But also you have the prime tens of the cycle of 11. And that prime tens are 7. They're gonna combine with the non-prime tens of the cycle of 3 and 7 to form more combinations of non-prime tens. So you're gonna have 4 times 21 and 7 times 18, because there is 18 non-prime tens in the cycle of 3 and 7. So you're gonna have 210 new non-prime tens combination. And we can remember that you're gonna have only 21 prime tens combination, the 7 of the cycle of 11 and the 3 prime tens of the cycle of 3 and 7. It's a beautiful process of making space for everything, for all possible combinations of tens. And after that, it will come the 13, the prime 13 cycle, and will combine with all of those. So really, the prime tens combinations are really pulled apart by the addition of non-prime tens. And prime after prime, they're gonna get pulled apart so far. So you can see that even the length of the cycles are growing very fast. This is in tens, right? The number of prime tens also grows exponentially. So you're gonna have lots and lots of prime tens combining. So every iteration has the same prime tens as the first one, right? So they're gonna have a lot of prime tens around. They're gonna have a prime ten at the beginning, prime ten on the end, prime ten on the middle in the symmetry line. But look, all these prime tens that are in all these iterations, they go far and far away from the gap. So that's what I call the not real part, because lots of them will not get to the real part soon. They will get to the real part later, when they combine with more cycles, and that's what's gonna make them go very, very far away from the gap. They will appear very far away. So look how small can be the gap. Even will be much more smaller than that. And look how far can be the prime tens. Imagine this cycle repeats like for a prime number, a big prime number, so of more than 100. You will have prime tens 100 times down when the gap is just at the beginning of the first cycle. The other iterations are far away. So that's what makes me to say that there is a part that is not a real part, right? Not in that moment, at least. You can see here the proportion of a gap to the length of the cycle in this table. You see how small gets the gap. That means that the gap is gonna be at a very tiny portion of the cycle as we go up in cycles. And also you have here the proportion of tens per tenth of cycle. And they get very, very small. This tells you how big gotta be the cycle and how separate gotta be the prime terms from each other. It's so big the length of separation between prime terms. That's why computer can see this, right? Not yet. Here you have the equation for the gap length, is this one here, and two computation for the gap. One is for the cycle of 3 through 19, and the other one from the cycle of 3 through 29. Here the gap decreases a little bit, but really when you go up in prime numbers, it's going to be increasing and increasing. What decreases and increases the prime terms? A diminishing in flips affected by decreasing proportion of primes. Decreasing change of the perfect cycle to the next perfect cycle. We're going to study that in the next slides. Overflip of not primes. Decreasing combination of non-prime tens with other tens, increasing distance between prime tens. Flip of potential primes and decreasing proportion of length of new cycle to gap of the length of the cycle. Some observations. New cycles can't flip all tens in a continuous process. It's a process of creating, making space. And we can see that any prime gonna have only 4 tens with numbers. The most important tendency to stabilize and repeat cycles, and for prime tens to not be pulled away forever, approaching zero change. Imagine you have an ideal prime with no numbers. That's not possible, but imagine. And it combines with another cycle. For example, a cycle of a prime, like this one, or any other cycle, the cycle of 3 and 7, or all cycles. So, because it has no numbers, what's gonna happen is that this cycle gonna repeat as many times as tens has this ideal cycle. So you're gonna get 7 of those here because this has 7, so you're gonna have 7 repeated exactly cycles. Any cycle merged with an ideally all full 10 cycle will duplicate exact copies of the cycle. You can see that here. If we merge together an ideally cycle of 3 tens with the cycle of 7, you're gonna have this. Here you will have the 7, here you will have the prime 10, the 1, the same as in the cycle of 7. You're gonna have repetitions of the cycle of 7, 3 repetitions of the cycle of 7. That's why I make this new variable. This is called stabilizations of cycles, and the variable v for duplicate. We have the prime m minus 4 divided by prime m. That will be the variable of duplicate. So we have in the cycle of 7 gonna be 0.428, cycle of 11 0.636, cycle of 23 0.7, and the cycle of 101, that is a prime, 0.96. In this cycle, this is a small number, 0.99999. So as we all go up in prime numbers, the cycles gonna be starting to look more similar to each other. And because they map the real number line, the real numbers gonna look more like the cycles, like the symmetry cycles. So you see here the cycles of single primes. As we go up, we're gonna have more prime terms. It's the prime number minus 4. As we go infinity, we are approaching an ideally full of prime terms cycle. So this is the length of the cycle, okay? This will be the length. And this will be the length of the last prime number of that cycle. For this cycle, this will be the length of 110. And these are the cycles that this length gonna repeat inside this cycle until it finishes. So this gives us an idea that as we are going up, more times the cycle of the new prime number gonna kick in. Anyway, as we go up, there's gonna be much more non-prime terms and much more numbers that are not primes, and the proportion of primes gonna get lower. And there is a balance. You can see if you take the proportion of the slope, right, of primes, the proportion of primes doesn't change too much from cycle to cycle. Even this goes higher very fast. So the length of the new cycle will be the length of the previous cycle times Pn, right? So this is the equation. That's always like that. We know that already. We now represent the number of prime terms in cycles, right, with the variable s. So the prime terms from the prime number 3 to the prime number n, the cycle, 3 through n, will be represented by the variable s. You have it here. So number of prime terms in the new cycle will be the number of prime terms in the previous cycle times prime n minus 4. And you have the formula here. They are very simple equations, basic equations. For a prime n equal 13, this is an example, we will have the cycle from 3 through 11 times prime n minus 4, and that will be the amount of prime terms that we will have. The cycle of 3 through 11 has 21 prime terms times 13 minus 4, that is Pn minus 4, will be 189 prime terms. So here we have the proportion of prime terms in a cycle. For huge numbers, we can get rid of the 4 and make this equation, just to make a comparison. We have the length equation here. So we're gonna do a proportion. We're gonna divide the number of prime terms with the number of the length of that cycle. And you can see that both are gonna be multiplied by prime n. So this is going to be, as prime n goes to infinity, gonna be more and more constant, gonna be more and more proportional. This means that the prime terms approach a constant distribution in the cycle as prime n goes to infinity, with a little increase in the distance between prime terms for new cycles forming. Same will happen to twins, because the equation of the proportion of prime terms to length of the cycle always is from 0 to the length and the number of prime terms of the cycle, approaching a constant proportion of primes. The amount of prime terms in the portion of the real numbers that had a bigger rate of change will get smaller and smaller until we approach closer to a constant proportion of primes as we go to infinity. This looks like or very similar to the predicted 1 over log x, but more studies will clarify this. Really, is a gradual process because there is a part of prime terms that are in the real number line, but it's gradually. But as we go to infinity, prime terms, twins, and the whole cycle gonna look more alike. Like we're gonna have something more constant, and we'll get stabilized. The real number line will approach a constant proportion of primes. The gap of each cycle will reflect the same proportion of prime tens as in the cycles. Prime tens will be approaching the same distance in the real number line as in the symmetric cycles. The real numbers will have the same composition of the cycles when Pn gets big enough. Same will happen to twin primes, and no prime number, because every cycle will look more alike. There will be an infinite number of tens full of primes. The cycle of primes are mapping through their gap the real number line. At very similar cycles with almost constant proportion of prime tens, the real numbers will look very similar to the cycles, with prime tens converging to the same distance of separation. We can see here how every cycle has a gap. We told this already. And how at the same time the cycles will be mapping the real number of line. But if all the cycles look similar, the real number will look similar to the cycles. Okay, this sketch is not representative in size, neither the gap, but we have here Pn and Pn minus 1. They're gonna look very similar, how you can see now. But this is at huge numbers, of course. But the one on top gonna be Pn times the one on the bottom. The blue one gonna be Pn times the red one. So gonna be much more longer, but similar in distribution than the red one. The gap gonna be behind always, but these ones gonna be mapping the real numbers. So eventually the real numbers are gonna be stabilized and gonna look more alike like the cycles. These two equations with the model of symmetry of the cycle of primes and its characteristics described in this video drives me to the conclusion that there is an infinite number of tens full of primes, especially this equation here and when Pn goes to infinity. Some conclusions. We approach zero chains as we approach infinity for an approach to a constant proportion of primes, twin primes and prime tens. Approaching constant slope as numbers approach infinity. Distance between twin primes and prime tens get stabilized. Cycles combines in all possible combinations in a symmetry process. There will be always tens full of primes. Check relations between Riemann zeta zeros and symmetric cycles. Check symmetry of cycles with 1/2 Riemann zeta function line and other lines and concepts. That's in the imaginary plane, right? Further study of the 3 model of cycles expansions shown in this presentation can be helpful. And you have there 2 prime tens, 2 tens full of primes. One is in the tenth of thousands and the other one is in the millions already. Numbers are a symmetric wave of primes to infinity. Thanks for watching. My name is Manuel P. Rodriguez Velasco. See you later.